A very good afternoon to all. I'm Meenakshi Gupta, Assistant Professor in IIMT College of Pharmacy, Greater Noida, is giving a video lecture on limit test. Now let us start with the limit test. So first of all, we'll give a definition of limit test. Actually, what are limit tests? So limit tests are quantitative and semi-quantitative tests designed to identify and control small quantities of impurities which are likely to be present in the pharmaceutical substance. Means to say that limit tests are some of the tests which are semi-quantitative, means that it is not giving us the total quantity. It is a semi-quantitative test, and that too by the comparison method, we identify and then control some of the impurities that might be present in the pharmaceutical substance. And that too impurities which might be present in the pharmaceutical substance are mostly the inorganic impurities present in the compound. And that too in the limit test, we do a comparison method, comparison with the standard and the test. As you can see here in the diagram, there is one standard and there is one test. So limit test is usually a comparison method. In that, test is a sample and standard is the standard solution. So we compare this test with the standard. So now the very most important question which comes to the mind is that why limit tests are important. For a pharmaceutical substance to be pure, it is very much important that a pharmaceutical substance should be it should be to a very high level. It should be pure. Why? Because the impurities that might be present in the test or in the compound that can be harmful for the consumption, so that should be avoided. That should be actually removed from the pharmaceutical substance. So, and another thing is that impurities should be at a very much defined level, to a level where it is 0.002 might be. So in ppm or whatsoever. So harmful impurities should be removed from the pharmaceutical substance. So that is why we carry out the limit test, and limit tests are very important in making the APIs or in further from the API formulations. So now the important question that comes into mind is, what is impurity? So the impurity in a pharmaceutical substance are the unwanted chemicals that remain with the API, that is the active pharmaceutical ingredient, or developed during the formulations. So it may be present, impurity may be present in the API or may develop during the formulations which we develop from the active pharmaceutical ingredient, or maybe that in the process of obtaining the API, in that process, both from the API as well as in the formulations, both impurities are possible. So we have to first identify the impurities and then remove them. So the presence of these unwanted chemicals, even in the smallest quantities, as I told, even in 0.002 milligrams, micrograms, or even the ppm, they are very important. So they should be removed because these are unwanted chemicals and they reduce the efficacy of the pharmaceutical products. So they should not be at 0.002% level also. So to have an efficacy and safety of the pharmaceutical products, we do not want the unwanted chemicals in the formulations or in the API. So the necessity is to remove these impurities in the pharmaceutical substance. So that is how we carry out the limit test. So limit test is basically identifying first of all the impurities and then removing it. So limit tests are the semi-quantitative methods. As I told, semi-quantitative method means here we are doing the comparison method, that we make two solutions. One is counted as a standard, the other counted as a test, and through the comparison method or through the virtual methods, using a dark background, we compare both of the standard and the test solution, and we see how much impurity is present in comparison with the standard. So now there are various other methods also to determine the impurities, and that is limit test. And of course, one important term comes into mind is ASSAY. So in this slide, I wanted to explain what is limit test and what is ASSAY. So limit test, as I told, it is a quantitative or semi-quantitative method to identify and control the small amount of impurities that might be present in the substance. And furthermore, it is a very useful method to identify the small amount of inorganic impurities like maybe heavy metals, iron, sulfate, chloride, lead. And so they have to be removed, first of all identified and then removed. So limit test gives us a quantitative and semi-quantitative, and that too in the semi-quantitative we have the comparison method. So by making the standardized test, we compare and so we identify the impurities. Now we'll take into account the ASSAY. Now the ASSAY is the method, or it is called as it is a way to identify the percentage purity. So now if suppose we have taken if we have taken a compound in that we want to measure how much pure the substance is. So in for that, measuring the percentage purity, for calculating the percentage purity, we do ASSAY. So ASSAY is basically more targeted upon the main functional groups that are present in the sample. And it is, of course, it can be like quantitative, semi-quantitative and qualitative. So ASSAYs usually gives us a quantity. So this much percentage, because it's a percentage purity. So it gives us the percentage, that this much percentage of the compound is present actually, and that too the functional components of the sample. So limit test and ASSAYs are like limit test, we determine how much amount of the impurities might be present in the sample, and ASSAY is how much pure the substance is. So this slide shows the comparison method. So now let us come on to understanding of what actually we do while we perform the limit test. So limit test for chloride. I've taken one example, 2-3 examples. So let us first go for the limit test for chloride. Here I have shown one reaction and the principle. So now the principle for limit test for chloride shows us that the limit test of chloride is based on the reaction of soluble chlorides with silver nitrate in the presence of dilute nitric acid to form the precipitates that of AgCl, that is silver chloride, which appears in the solution, and that actually gives us the turbidity or the opalescence. So basically in the chloride test we get the opalescence. Now we will discuss what is turbidity and what is opalescence also. Now first of all, let us discuss more appropriately, more broadly upon what the reaction says. Now in the limit test for chloride, as it is a limit test, we are finding out the impurities of chloride in our sample. So first we make two samples, two solutions. One is a standard and another is a test. So chloride, basically what happens, all the impurities as in chloride now will react with AgNO3. We are adding AgNO3, that is silver nitrate, in the presence of dilute nitric acid. It forms AgCl, and this arrow shows that is a precipitate. So that forms the white color precipitates. So this precipitates appears in the solution, and that gives it the opalescence. Then what is the actual procedure that we follow? The procedure followed here is that we make two solutions. One is counted as a test, another counted as a standard. So test means here we have taken the sample. Sample means that the compound in which we want to see the how much amount of the impurities are present. So here we are carrying out the chloride test. So the sample will take in which we have to see how much amount of the chloride impurities is present. Or we can take an unknown sample also in which to see what. So because limit test gives you the method to identify, so we can take an unknown sample also and can perform the various tests to know the amount or the to identify chloride, lead, heavy metal, or arsenic, those types of impurities that might be present in the sample. So here we have taken this procedure is for the limit test for chloride. Here we have taken the test. So test gives that, and these all the tests and the standards are made according to the pharmacopoeia. Standards basically are given in the pharmacopoeias that when we are performing the limit test for chloride, how much amount of the standard solution has to be made. This is given in the pharmacopoeias. And the sample also, how much amount of the sample needs to be dissolved in water, that is also given in the official books. So now here we are taking 1 gram of the sample and dissolving in 5 ml of the distilled water. Then the test solution, then we add dilute nitric acid, then we add 1 ml of AgNO3 solution, that is silver nitrate, and we are going to do this in the Nestle cylinder. So now another important point here is that all the limit tests are carried out in the Nestle cylinder. So Nestle cylinder is a cylindrical shape in which limit tests are carried out because it is made up of glass and it is very much possible to see through. So that is why we use the Nestle cylinders and is typically made for carrying out the limit test. So we dilute, we can take up to 50 ml or 100 ml Nestle cylinder. Here we have taken 50 ml Nestle cylinder because quantities were small. So we have added to the sample 10 ml of dilute nitric acid. To this we have added 1 ml of AgNO3, and then this is being diluted to 50 ml. And of course we use the distilled water in this. After diluting this to 50 ml, then we stir it with a glass rod and keep it aside for 5 minutes. Then we of course measure its turbidity or opalescence. And the standard solution in the next this we take a standard solution in the next or in another Nestle cylinder we take a standard solution, and standard solution for limit test for chloride is made by taking 1 ml of 0.0584% weight by volume of NaCl. So that gives a standard solution for limit test for chloride. Here the quantity is specific because this is a percentage weight by volume of NaCl, because this is a standard and standards are all officials given in the pharmacopoeia. To this also we'll add the 10 ml of dilute nitric acid. To this we'll add 1 ml of AgNO3 solution. To again this is diluted to 50 ml in the Nestle cylinder, and then this is stirred with the glass rod. Also this is kept aside for 5 minutes, and then the turbidity or the opalescence is measured. As you can see in the diagram, we have this as a Nestle cylinder. This is a representation of the Nestle cylinder. So one is marked as a test, another is marked as a standard. So procedure is followed for test and procedure is followed for standard. Then what we do is we keep this as for 5 minutes. After 5 minutes, we observe this against a darker background. So observation, noted the turbidity and basically the opalescence in the test solution against the standard solution. So now I wanted to explain you what is turbidity and opalescence. What is the difference between the both the solutions when precipitates have been formed here, because precipitates are formed of AgCl. Like when we are talking about the limit test for chloride, AgCl precipitates are formed. So the thing is that in this solution, AgCl precipitates will make the solution turbid, right? And now what is the difference between turbidity and opalescence? That when the solution appears, when the solution is having the precipitates inside it, so now what will happen is that the solution will appear to be turbid, right? Opalescence means that we can see through it. Turbidity we can see through this glass or we cannot see, but the opalescence means that the solution will appear to be opaque and we can see through. So the opalescence is usually measured in the limit test for chloride, and the standard solution of course give us a standard solutions which is official. So it will give us the appropriate amount of the chloride impurities that might be present in the sample. So now what we have to do is we have to compare it with our sample. So sample is test. So if we see, we put this against the a darker background to see visually which is having the more chloride impurity. So opalescence is seen in the standard and is compared with that of the test. So if we see standard is having the more turbidity or the opalescence than that of the test, so that means uh, the test passes the limit test for chloride. That means the test turbidity or the opalescence should be less than that of the standard. If we observe this, that the test opalescence or the turbidity is less than that of the standard, then our sample passes the limit test for chloride. If it appears to be more, in the case then if the test appears to be more turbid or opaque, then the sample fails to pass the limit test for chloride. Now, what are the specific reasons that turbidity is obtained or the opalescence is obtained? It is why, because in this reaction itself, what we're talking about here, nitric acid is added to the limit test in which we are taking the silver chloride. So that helps, actually nitric acid being an acid, so it makes a solution more acidic and helps silver nitrate to form more of the AgCl precipitates. So that makes a solution turbid in the end process. So this is what we do actually in the limit test for chloride. The next example we have taken is the limit test for sulfates. Now, again, there is some reaction which follows the basic principle for the limit test for sulfate. So the basic principle here is that sulfate impurities that might be present in the sample, they are being treated with the barium chloride, BaCl2, in the presence of dilute H2SO4. It gives the BaSO4, that is a barium sulfate precipitates, and that precipitates gives us a turbidity. So the reaction that follows is that sulfate impurities in the sample, in the given sample or maybe the unknown sample, to this we are reacting the barium chloride in the presence of dilute nitric acid or acetic acid also we can use. It forms a barium sulfate precipitates, and that precipitates gives us the turbidity. Now let us see what is the procedure behind this. Again, procedure, we have to make the standard and the test as usual. So both are taken in the Nestle cylinder. Now here the standard solution in the limit test for sulfate is made by taking 1 ml of 0.1089% weight by volume solution of potassium sulfate, or we can also take as a sodium sulfate. So both with both potassium sulfate and sodium sulfate, we can make the standard solution. The quantity is specific, 0.1089% weight by volume of the potassium sulfate, and that is taken in the Nestle cylinder. Then to this we are adding 2 ml of dilute acetic acid, or nitric acid can also be added. Sorry, sulfuric acid can also be added. They both gives us the solution acidic. To this we are adding 5 ml of BSR. BSR is barium sulfate reagent. Barium sulfate reagent basically is having the barium chloride which actually reacts with the sulfate impurities. And we have K2SO4, that is a potassium sulfate, and also alcohol added to this. So alcohol actually helps in preventing the supersaturation, so that all the precipitates are forming the turbidity. So BSR is an important ingredient, important solution that we add into the limit test for sulfate. So BSR, which is a barium sulfate reagent. And then after adding the dilute acetic acid or the sulfuric acid, we add 5 ml of BSR reagent in which barium chloride actually reacts. To this Nestle cylinder, we add 50 ml of distilled water. Shake it with, stir it with a glass rod and keep it aside for 5 minutes. We observe the turbidity after 5 minutes. And the standard test solution is made by taking 1 gram of the sample solution, again dissolving in the water as per it is written in the pharmacopoeia, as per it is given in the pharmacopoeia. Then we add 2 ml of again acetic acid. To this we add 5 ml of BSR, that is a barium sulfate reagent in which barium chloride is actually acting. To this is again diluted to 50 ml with distilled water in a Nestle cylinder, stir with a glass rod and kept aside for 5 minutes. And after 5 minutes, we observe the turbidity against a darker background. Now again, this looks like the representation what we have made, the standard and the test. So this is carried out in the Nestle cylinder. Again, with a comparison method that we compare our sample with that of the standard, and so we see how much amount of the turbidity is present in the test or the sample against the standard. So the result should be that the test should have the lesser turbidity than that of the standard. If the test has the lesser turbidity than that of the standard, then the sample passes the limit test for sulfate. In case the turbidity appears to be more in the sample, then our sample fails to pass the limit test for sulfate. As per IP, this is all the procedures. Procedure is as per the Indian Pharmacopoeia, that is IP. Now we have another example of the limit test for arsenic. So arsenic is counted as the major type of impurities that might be present and that is harmful. So we need to identify the arsenic impurity, the lead impurity, the iron impurities, and then to remove this. So now let us discuss about arsenic. So while carrying out the limit test for arsenic, the basic principle followed is understood by the apparatus in which we carry out the limit test for arsenic, and that apparatus is called as a Gutset apparatus. Now Gutset apparatus looks like this, that it has a bottle, round bottle, and there is a tube which has a hole inside at the where we have put the solution. So there is a hole, and this moves up, in which we have two rubber bongs, and in between that rubber bongs we have the mercury chloride paper attached. So now what happens here, we can see a lead acetate wool plug is attached over here, lead acetate wool plug. So now what happens, that we take a solution in which we have arsenic impurities, might be present or might not be also be present. So we take the sample solution in which arsenic as an impurity is present. So now that reacts. So we have here the reaction. So now what we add into the solution is that arsenic as an impurity is present in the sample. Now to this we add zinc and also the HCl. So now the basic reaction which goes is that zinc reacts with HCl to form ZnCl2 plus 2 moles of nascent hydrogen is formed. And this nascent hydrogen actually reacts with arsenic. So arsenic is also reduced to the state of 5 plus to 3 plus. So after this, the nascent hydrogen reacts with arsenic to form arsine gas. So ASH3 is actually the arrow shown upwards. So this is a gas. So arsenic gas is formed, and this gas actually goes to the mercury chloride paper. So here we can see the reaction that arsenic gas goes to the mercury chloride paper to gives us the stain on the mercury chloride paper. So HDCl2 twice ASH3 is a complex that is formed, dimercurate complex, which gives a yellow color stain on the mercury chloride paper. So the yellow stain on the mercury chloride paper gives us the yellow stain on the mercury chloride paper gives us actually the method to identify the impurities. So if we get, so I'm showing the diagram again over here. So if we have this solution in which arsenic impurities is present, so arsine gas will move from this hole in the upward direction. Here we have made an lead acetate plug because with the arsine gas, some amount of hydrogen sulfide gas is also been formed. So this lead acetate plug that absorbs all amount of the hydrogen sulfide gas that is formed. So only the pure arsine gas which is formed from this solution. In solution we take zinc, HCl, and the solution in which arsenic impurities is present. So arsenic impurity with the zinc and the HCl, here arsine gas will be formed, and that arsine gas now will move upwards and react with the mercury chloride paper. And when it reacts with the mercury chloride paper, it gives us a yellow stain. So the standard and the test, that is a sample, are both compared for the amount of the stain that is produced on the mercury chloride paper. So here what we note is the color intensity of the yellow stain on the mercury chloride paper. So this color intensity is compared with that of the standard and the test. The various reasons to add all this type of why do we add the stannous chloride, and why do we add the zinc, potassium iodide, and the stannous chloride? Because it acts as a reducing agent. HCl acts as a solution to make it acidic. Lead acetate plug is used to absorb the hydrogen sulfide gas that is formed. Only the arsine gas should react with the mercury chloride paper. Now let us move on to the another limit test, that is the limit test for iron. This has basically been on the reaction. The principle is based on the reaction that iron reacts with thioglycolic acid, which is CH2SH. That is whole twice of CH2SH, and with the because it's an acid, so COH. So this is thioglycolic acid that forms a complex which is called as a ferrous thioglycolate complex. With the thioglycolic acid, iron forms the complex, and that too in the ferrous form. So ferrous thioglycolate complex, which is a red in color, this also goes from pink to reddish in color. So the intensity of the color from the pink to the red is measured with that of the standard. So the basic reaction or the principle which follows is that the iron reacts in the presence of thioglycolic acid. It forms a ferrous thioglycolate complex, which is pale pink to deep reddish in color, or may also be purplish in color. So we have to measure the intensity, whether it is a pale pink or whether it's a purple. So the procedure which follows again is the standard and the test. Again, this is carried out in the Nestle cylinder, as the arsenic was carried out in the Gadzet apparatus. All the another can be carried out in the Nestle cylinder. So the iron limit test for iron is also carried out in the Nestle cylinder. Here we take the standard solution as ferrous ammonium sulfate. It is dissolved in 10 ml of sulfuric acid diluted to 100 ml. To this we add the citric acid also. Then the thioglycolic acid. Make the solution alkaline with ammonia. Only because we have added so much of the acid that it has to be neutralized with ammonia, and that again is diluted with 50 ml with the distilled water in the Nestle cylinder. Shake, stir with a glass rod, and keep it aside for 5 minutes. This test is also taken. The sample is again dissolved in water. To this we add citric acid, we add thioglycolic acid, make the solution alkaline with ammonia, and diluted with 50 ml of distilled water, and stir with a glass rod. Keep it aside for 5 minutes. Again, here we note the color intensity, because again I said that the complex which is formed of ferrous thioglycolate, it is deep reddish to purplish or maybe pale pink. So the color intensity, whether it is a pale pink or it is a deep reddish purplish in color, so that we compare with the standard. So standard and the test is compared. This is how we carry out the limit test for iron. So basically the reaction here is with the thioglycolic acid to that with the citric acid. Now citric acid and ammonia actually prevents the precipitation of being key, like ammonia can precipitate the iron and can evaporate. So citric acid actually prevents the ammonia to react with the iron. So this is how we add the citric acid. So citric acid further also helps all the ferrous ions, the ferrous ions can combine with the thioglycolic acid to make the ferrous thioglycolate complex. So that is how we get the pinkish color here. And that pinkish color to the red or the purplish color can be compared with that of the standard. So like this, we can take out the Nestle sliders and we can see the comparison with the standard. Thank you so much.